Hello, my name is Rhea McElroy, and this is my lab report on Physics 2211's Lab 1 over constant velocity. In this report, I will go over an introduction, models, the experiment, the code for the experiment, a discussion, and a conclusion. To start, the purpose of this experiment was to observe the motion of an object at constant velocity / with a net force of 0, and compare that motion to the predictions of a computational model. Some physics principles that are evident throughout this experiment are Newton's first and second laws and constant velocity. Newton's first law states that an object in motion or an object at rest will stay in motion and rest, respectively, unless a net force acts on it. Newton's second law derives the equation force equals mass times acceleration, which will be used in future calculations during the course of this experiment. And finally, constant velocity simply means that the net force is equal to 0. Thus, according to Newton's first law, velocity remains constant. These are the models or formulas used for this experiment. The velocity update formula, where Vf equals final velocity, Vi equals initial velocity, A is for acceleration or net force, and delta t is the change in time, is important for the computational model. Because the net force is 0, due to constant velocity, the model will maintain the same velocity for each calculation. The position update formula, where Rf equals final position, Ri equals initial position, VAVG is equal to average velocity, and delta t is equal to change in time, is also useful for the accuracy of the computational model, as it will show how far the object moves at a constant velocity over time. Newton's second law, force equals mass times acceleration, is important for deriving our net force, which is again 0. And lastly, the average velocity formula, where xf is final position, xi is initial position, tf is final time, and ti is initial time, is essential in calculating the initial, and thus final velocity, since velocity is constant, that the computational model will use for its calculations. The object utilized for this experiment was a marker, which acts as the system. The surroundings include both friction and air resistance, both of which shall be ignored for the purposes of constant velocity. To conduct this experiment, we recorded a marker moving at a constant velocity at a perpendicular angle to its motion. For future reference in the tracker app, we included a meter stick and frame. We then uploaded the video into the tracker app and used the calibration tool to determine the position of the marker according to time. We calculated the constant velocity of the marker using the information from the tracker app and plugged this number, as well as the initial position, into our Glow script code. Finally, we compared the two datasets with Excel. According to the tracker app, the total distance traveled by the marker was 0.647 meters, and the total time the marker moved was 1.3 seconds. The initial position of the marker at time equals 0 was 5.155 times 10 to the negative 3 meters. Using this initial position and then the position and time recorded second, we found the average velocity of the marker to be 0.495 meters per second according to the average velocity formula. Because we are foregoing outstanding factors such as friction, the use of the second position rather than the last should be more accurate to what constant velocity would look like, as the velocity will have slowed down over time otherwise. Here's the code plugged into Glow script. The initial position and initial velocity come from the tracker app and the calculations done using the tracker app's data. We start at time equals 0 with the time increment of 0.033 seconds and an end time of 1.3 seconds, which, once again, comes from the tracker app. To ensure constant velocity, we set the net force equal to 0, so that when the computational model runs through the velocity update formula and the position update formula, velocity does not change. Glow script running the position update formula using our data creates numbers or positions that we can compare to the tracker app. Here are the individual graphs of each app's data showing the position of the marker related to change in time. On the left is the tracker app and on the right is Glow script. Now, here is both of those data sets in one graph. The lines are almost identical, which demonstrates Newton's first law, in which, when net force is equal to 0, velocity is constant. This graph also shows that our calculations are fairly accurate. Any differences between the lines are due to either human error, in which something was miscalculated, measured incorrectly, or recorded at an angle, or due to factors we didn't consider, such as friction and air resistance. Now for some additional questions. Discuss briefly how your results would change if you did not flip the axes. Had these axes not been flipped, all of the numbers derived from the tracker app would be negative. Velocity would have been negative 0.495 meters per second instead of positive 0.495 meters per second, and other values such as slope and position would have changed too. Second, is it possible for you to say how many forces are being added together to give 0 net force in the case that you observed? The answer is no. Though net force is 0 due to constant velocity, 0 doesn't mean there aren't any forces, but that all of the forces sum to 0. Though, because we can't see these forces, it is impossible to tell how many there are or their values. In conclusion, although we could not entirely simulate constant velocity, this experiment demonstrated that we can estimate it and prove Newton's laws, and that constant velocity means the net force is equal to 0 nonetheless.